Sound is great.
你俩认真听还是
Is your audio on here? Give me like my mic should be on here lah. Or you want to is this still breaking now? I cannot test one. Oh, better. Breaking better. Audio. Yeah, so be careful. That's like a mic. Can you hear me? Can you hear me? Yeah, it's good. Okay, nice. Like so. Okay. So, 不用
用啊，还是挺少人。
you're ready.
Hello guys, we'll be starting the seminar now, and we welcome our speaker today, Larry. Yeah.
Okay, so so greetings everyone. I'm Larry Kong-Ting-Sen, and well, today I'll be talking about like a little bit about hypersurfaces, mostly about dimension and some other stuff that I have to like basically prepare in advance before actually being able to talk about. Like there's actually surprisingly a lot of stuff I have to prepare first that may not be covered in an AA1 course. Okay, so like we'll start it off with a little bit of hypersurfaces. So basically, if you recall last Thursday, that well, basically like just the last two weeks, we basically introduced like algebraic sets and all that stuff. And today we'll be looking at we'll start by looking at one specific type of algebraic sets, specifically hypersurfaces. A hypersurface is an AN is the set is the zero set of one and only one polynomial. And so yeah, this is basically the definition of hypersurface. And if I remember correctly, last Thursday, that we say it is if it is say like a polynomial of one variable, it's something like a fine line, and two is a fine curve, and so on. So in general, this is what a hypersurface is. And furthermore, if f is irreducible, then in fact we have not just we have a variety. And there are some examples of hypersurfaces. Among those that are a little more well-known ones, there are like say the conic sections, like fx equals to xy, say. And there are also specifically hyperspheres or n-spheres. That is basically like say that is basically like given by fx fx1 f2. Yeah, So these are some examples that like, and there are more that is basically just like one polynomial of few variables. Like that's basically what a hypersphere is, hypersurface is. And we have a little bit nice theorem about inclusion, some sort of inclusion of between hypersurfaces and the algebraic set. That is to say, if A is the zero set of some zero set of the zero set of some ideal of the polynomial ring, and H is a hypersurface. Then we have the following. And in fact, this is basically one direction is quite easy to see. That is to say, this direction is basically if Fm is in J, or specifically the ideal generated by J, not just J itself. So basically, if there is some Fj, Fm, there is indeed some power of this, then this means that we have for any p, then for any p in A, that is Vj, then we have Fm p equals Fm p equals to 0. But this basically, since we are like say in a field, then it's basically just Fp equals to 0. So all right. Which one? Oh, is it? Comment. Oh, okay. Yeah. Yeah. So basically, what we are shown here is that any root of any like the zero set, how do I say this? Is basically like any p in Vj also satisfy this. So specifically, let us say p is in the zero set of this f. So then this basically just says that Fj is a subset of, which is basically A H. And now for the other direction, it's basically we actually basically just use the Nostelensatz. So if A is a subset of H, this means that any point of A is a root for F basically. So then P and H just simply means Fp equals to Fp equals to 0. And this holds for any point of A. So this in fact means that F basically just vanish at Vj. So F is like so in other words, we basically say that F is in the ideal given by V of J. But this is precisely just the Nostelensatz basically says is actually just the radical of J. And this by definition basically just means that Fm is in J, like the ideal generated by J specifically. So yeah. So basically that's both ways going. So we basically have the relationship between us a regular algebraic set and a hypersurface, and when it holds. All right. So that's a brief detour to hypersurfaces. So now, before I talk about dimension, I have to introduce some new concepts. Let's see. Okay. Okay. So we have to talk about what does it mean. What we have to talk about like algebraic extensions and like algebraic independence and dependence, etc. So first so our setting is we let A be a K algebra. And let's say alpha 1, alpha 2, and so on are elements of A. So, and of course, K is a field. Then we say that these elements alpha 1, alpha 2, and alpha n, they are algebraically dependent, or just for short, algebraic over K. If there is a polynomial, if there is a polynomial, specifically, if there is a polynomial such that f, f alpha 1, alpha 2, so on, equals to 0. So basically the idea is like, if like everyone here has taken linear algebra at this point, right? So like, we say that a given set of vectors are linearly dependent if there is there are appropriate not all zero coefficients such that the linear combination of them equals to 0. And in some way, this is basically a very similar deal. We say that these are algebraically dependent over K if there is like say there is say a non-zero polynomial such that all of them become 0. Actually, hmm? Uh, hmm? Oh, right, yeah. Right, thank you. Yeah. And if there are no such polynomials such that these elements are not there are no polynomials such that they are algebraically dependent, we call them algebraically independent. Or you may also heard of this term, transcendental. So for some examples, you might have heard of like the term transcendental numbers. These are basically like numbers that cannot be written as the root of some polynomial. Like for example, e and pi are among them. In this case, what we say that like this e is transcendental over q, I think. Yeah, q. Because though there are no polynomials with coefficients from q that can actually like make e a root of such this polynomial. The proof is well, I would not bother writing it. It is actually quite complicated, and pi as well. But as for a fun fact, we actually do not know like if e and pi like say like are they like we know that e and pi are transcendental numbers by their own right, but we actually do not yet know that if like say e plus pi or like e pi like we know one of them, at least one of them must be rational, but we actually don't know like if both of them are irrational. It's something like basically showing this is kind of hard, but okay, so let's get back to the point here. So now we talk about like say we consider like, well, we briefly talk about extensions, field extensions. So basically like now we let omega be a field, and let's say k is also the field, and in fact omega contains k. So here we say that, well, k is a subfield omega, or sometimes we say that like omega is a extension field of k. That's to say like basically we have, and sometimes denote this, we denote this fact with omega slash k, omega over k. So basically it's like we consider k and then we extend it to become omega. There we go. And for this, no, not it doesn't mean quotient in this case. Yeah. And for now, and we also introduce a new notation. If we have say any subset of omega in this case, we denote we denote Ka to be the smallest subfield of omega, such that it contains K and A, both of them. And as for an example, right, so as an example, if let's say A consists of x1, x2 until xm, then Ka, then in this case, Ka consists of all the quotients, K consists of all the terms like this. Sorry. Where F and G are in K. Basically, what we do is just like you have this element, you have the elements of K and A individually first, and then we just add as little as possible until it becomes a field. Basically, if they add together, we do that, and then the multiplication and the inverse and such and such. So for something like this, Ka is basically just like the quotient of all possible quotient, and basically the polymers are there just to represent all the possible ways of add, subtract, multiplying, dividing, and such. And we have another one, a subset B of omega, like a subset B of omega, which just now we talk about what does it mean for elements to be algebraic over a field. Now we talk about what does it mean for like say two subsets to be a subset to be algebraically dependent on another subset given a bigger field. So a subset B, subset of omega, is algebraically dependent on A if for any element B, for any element in B, this element, say y is algebraic over Ka. So basically like you have so basically that's to say like there is a polynomial there's a polynomial based with coefficients from Ka, not just K anymore. So, so in fact, there is like a kind of like similarity between this transcendental extension basis and stuff and the linear algebra stuff we have. Specifically, we actually have something like this. Okay, so let's say we are working under omega, which is we are working under omega, which is an extended or which is a few extension of K, and then we have two subsets, A and B. Then if we have A is algebraically independent over K, and two, A is algebraically dependent on B over K, then we in fact have M less than or equal to N. So basically, if we have a linear algebra analog, which is given as such, basically like you can read algebraically independent, to be kind of straightforward, meaning of linearly independent. And this algebraically depend on a set, or we can say this one is in fact, by definition, this one is in fact basically just saying that A is A is algebraic, specifically is algebraic over KB. And so we have a linearly independent analog, and we also have a span analog. In this case, this is basically precisely a second condition. Basically, that is to say, like, let's say A is linearly independent. A is algebraic. A is algebraic over KB. Basically means that in some sense, like, you can think of it as like the B, in some sense, it can say span A, but like to make it more precise, it basically says that any element, basically like any element of A, we basically can just write it as a root to a polynomial with coefficients from the subfield KB. So in this, there is in some sense like basically just using B, we can span over the A, in the sense that we basically can write them just becoming the solutions of roots, the solution of polynomials with coefficients from KB itself. So of course, in linear algebra, we also have the concept basically that a linearly independent set always has less than or equal, the number of elements in a linear independent set is always less than or equal to the number of elements in a spanning set. Yeah. So basically just we also have a similar result here, which is basically like if you have two sets, we have two subsets of a field, and one is algebraically independent, and one is algebraically independent over K by its own right, and one is that it is algebraically dependent, it is algebraic over the field KB. Then we similarly have the result that like the number of elements in the A is less than or equal to the number of elements in B. So yeah, I'm just gonna analog for basis. We will get to that real quick. Actually, in fact, we'll get to it right now. In fact, what we have is a transcendence basis. So transcendence basis for omega slash k is is an algebraically independent subset. Let me. It might be better to write this. Okay, if A is a transcendent basis. Okay, if is over K, and 2 omega is algebraic. So basically, like the idea of basis in linear algebra, we also have a similar analog, which is basically again just these two conditions combined. That is, we have A is a transcendence basis for omega dash K if A is algebraically independent over K, so like it has the linear independence, so to speak. And 2, that omega is algebraic over Ka. Like you remember that K and A are both subsets of omega. So for omega to be algebraic over Ka is in some sense basically saying like just using K and A and just saying we want the roots of polymers with coefficient from here can actually reach all the elements from omega. So we once again have some results which is actually quite familiar to basically, which is if you take the time to properly translate to linear algebra, it is quite familiar actually. So we have, let's say, the assume. All right. And we assume there is a finite subset. So we assume there's a finite subset A of omega, such that omega is algebraic over Ka. So in some sense, basically, in linear algebra terms, the analog is that we have a finite subset, and such that the A itself can already span the omega. So then, what we have, our first result is that every maximally algebraic I'll just write TB for transcendent basis. So every maximally algebraically independent subset of omega is a transcendence basis. So it's basically like if we like look at this linear algebra analog, it basically says that like the biggest like linearly independent possible set is a basis for vector space. So similarly, every maximally algebraically independent subset of omega is a transcendent basis. So of course we have the other way around. That is to say, does every smallest every subset of A, every like minimal, that is minimal, that is so what we have here is basically like if we translate to linear algebra speak again, basically like the smallest spanning set for vector space is a basis for vector space as well. So similarly, every subset S of A such that it is both omega is algebraic over Ks, and this S is as small as possible, it also becomes a transcendent basis for omega. And of course, we finally have this important result. If you remember your linear algebra courses, then you should remember that basically all bases for vector space, they have the same number of elements. In fact, in linear algebra, this is what we call the dimension of a vector space. So we have something similar as well, but it is not yet the dimension for like the algebraic sets we have. So now, we call this value the transcendence degree. Let me write it down first. This is called the transcendence degree. And there are some notations, but usually I see it's written with TR degree. TR degree. Basically, it's like how many basically it's in some sense like how many elements do we have to like include into K until this field becomes omega itself. To put it more precise, like how do I say this? Okay, an example might work better here. So like you can see there is let's see, okay, so basically like okay, so a field. So let's say we have like say a polynomial ring, and we want to look at it as from just K itself. Then in this case, the transcendent degree of K of K x1 x2 to xn over K is actually just n. It's basically like first you have the field, but the x1, x2, and xn are basically like if we treat them as just like this indeterminates, then basically like none of them can be written as the algebraic. None of them can be written as a root to a polynomial only using K. So to introduce this, so we basically have to introduce like x1, x2 up until xn into like K in order to like basically get this. And we have pretty interesting results about this transcendent degree. if you have K, L, omega, if you have fields going like K is a subset of L, subset of omega, then in fact what we have is a pretty interesting fact. The transcendent degree of omega over K is actually the transcendent degree of K, L over K, plus the transcendent degree of omega over L. It's like basically like just pass it around and we get this result here. Yeah. For this one, what should I like that space? I'm not too sure. Okay. Basically, for the proof idea, at least for the proof idea, is basically like A union B, like let's say if A is a basis TB for the idea for the proof, but I will not elaborate here, is basically like, if they are both like if A is a transcendent basis for L, K, and B is a transcendent basis for omega over L, then it follows that A union B is a transcendent basis for omega over K. But I'll leave those details for those who you are interested in it. Yeah, homework. Okay, so all right. So before we almost get into dimension itself, let's talk about like so in A1, if you have taken A1, you probably have learned something about that is called like the field of fractions. Basically, like how we can go from Z to Q. There is a like in a way generalize it in a way such that like we make it from just Z to Q to any integral domain into a field. Basically, we just like allow the division, like basically define it that way. So now I will also do that for something a bit more general, which is basically the ring of fractions. So first, we have is like we consider a multiplicative subset. So what's a multiplicative subset? Ring. Okay, what you say? Let's say so S is this if S satisfies two properties. First, we're talking about ring with identities. If the multiplicative identity is in S itself, and two, if multiplication is close in S. So from here, what we have is that we actually can define a notion of we can actually define an equivalence relation between them. That is we can define like AS to be like, let's say, and we basically define it as this. We say that these two are equal if and only if there is like some u, u in S, such that u times at minus bs equals 0. Okay. And usually for like the field for nicer fractions, basically we only need like if we want to do this, usually we only need like at minus bs equals 0 perhaps. But in here like we require this basically because like we may it is not always possible to like cancel out u, so we make it a little bit more general. That's as long as there is such a u such that we can do this, even though at minus bs itself might not equal to 0, it at least equals to like a 0 divisor. So basically, yeah. And so yeah, very similar actually, yeah. It's basically a field fraction, but we go a little bit more general. And we call this A over S. And of course, we can define addition and multiplication in the same way you define it for rational numbers. So basically just this, and AS times BT is basically just ABT. Yep, just as intuitive as a thing. And you can check I'll probably leave it as a homework for you to check that these operations are in fact actually like well defined. That is like well defined in the sense that they do not depend on like if I write it as AS or if I write it as BT, if they are both equivalent, then the result I give you are like equivalent in that sense. And it also defines a ring. It also defines a ring. We call it this, where it's basically like and it is also this with this ring, basically the collection of all of these equivalent classes. But under the addition and multiplication that we define, they are basically the same. They basically actually just the same. It defines a ring. Yeah. And in particular, we want to use this mainly because there is a there is something that might be helpful with using this, which I will basically write it down now. So if S is a multiplicative subset of ring, then we in fact have a correspondence between, say, prime ideal. There's actually a one-to-one correspondence between these two. And the more explicit, if we want a more explicit map, is given by like say P. As it turns out, yeah, which is exactly just this. Hmm. Alright, so I think that is basically the preliminary results that I have to introduce before we get into dimension. Well, yeah, basically like that. So, but to reach that point, we first talk about like we first like if you recall the last 2 weeks, this algebraic this affine space can be thought of as like can be thought of with a topology, basically the Zariski topology specifically. So for this we'll talk a little bit about topology before we get into the definition itself. A topological space X is Noetherian if it satisfies a condition, the descending chain condition specifically. DCC for descending chain condition for closed subsets. That is to say, So say if let's say we have for any sequence, for any sequence, to for any sequence of closed subsets, basically like we have a sequence and all of them are like y1, y2 ordered by this inclusion. Then we have some m, we have m such that eventually the sequence is constant. Or to put it basically in more directions, basically a topological space is Noetherian if there are no sequences, there are no sequences of closed subsets ordered by inclusion that is like strictly descending. That is, it eventually has to like stay constant in the sense that like we basically just equals to the style like that. Or in other words, basically like if we require this set inclusion to be strict, then the length must be finite basically. And as it turns out, so an equivalent condition is that not equivalent condition, but it turns out for Noetherian spaces, this Noetherian space X can always be written as a finite union of irreducible components. And what do I mean by that? So basically, that means that it can be written as x1 union x2 until union xn, where each of these xi are closed, are proper, and in terms of and they are maximal in the sense that like it is not the superset. It is not the subset of some larger closed subset of X, basically. Okay, but of course, why did I introduce the concept of Noetherian to begin with? That is because, of course, the Zariski topology on AN is in fact Noetherian. And yeah, I go through this proof. It's pretty simple enough, actually. Okay, so let's say we have any descending chain of the closed sets of AN. In this case, that is basically the algebraic sets. So, what we do is we basically like take the ideal set on this algebraic sets, and if you remember by inclusion reversion, this means we have this. And now this is an ascending chain of ideals. This is an ascending chain of ideals for this for the polynomial ring. And here we use a result. We basically use a result here. In case you don't remember, week 1 we talk about Noetherian rings as well. And one of the definitions is that it satisfies the ascending chain conditions, which is basically just like descending chain conditions, but it's instead of go down, it's go up in terms of set inclusions. And as you can see, from week 1 we also have that so K is a field, implies that K is Noetherian. And K is Noetherian further implies that the polynomial ring is also Noetherian. So this, of course, means that we have some, we have some, we have like that. Basically, there is some point where where this sequence becomes constant. So let's say it's basically like at ym from like say ym onwards, then it's basically constant, just like this. Yeah, this is given by the fact that this ring itself is Noetherian. And what we can do is we can take the zero sets of these, and since these yms are actually algebraic sets, what we actually have is basically just we just undo it and get back this. Well, this same m is precisely what we need to show that this topology on AN is Noetherian. So now we have a good notion to like say introduce a concept of dimension. This is dimension.
Usual Euclidean topology. That
Euclidean, usually Euclidean topology. I'm sure it's generally, it's generally not. Actually, I think not. So as an example, if you want to, we can take like say, we can say consider this, and basically what we can always do is basically just like say 1.5. The usual Euclidean topology is not, because like you can make it as arbitrarily small and all of them are distinct. There's no way to like basically fix them. Like there are sequences that basically become constant, but we can also find a sequence that is never constant. So in this case, the Euclidean topology is not here. Yeah. So let's say we have a Noetherian space. Then since we know that like basically, so let's say we have like, so what we have is basically like let's say they're not equal, and let's say then none of them are like equal. They're like the inclusion are strict, and let's say, and because we know like by definition Noetherian space, this must eventually like stop somewhere. So let's say it stops at D. So now we introduce the dimension of this Noetherian space. Dimension of B is like, it's not D itself, but it's the supremum or or in this case maximum, or supremum of the length of chains. So this is so like basically like there are these chains that are closed and irreducible. In for this topological space, irreducible simply means like it cannot be written as the union of two proper subsets, proper closed subsets, if I remember correctly. So basically, there are like chains of many different lengths. We basically just say, okay, what is the longest possible chain? That we call the dimension of V. And the of note is that you notice that our V, we start at V0, so until V3. So basically, it's saying like we count the number of inclusions, not the number of sets itself. and remember that just now we talk about how Noetherian spaces, they're basically like it's a finite union of irreducible components. So in fact, what we have is a result basically saying that the dimension of this result is basically just the maximum of the dimensions of the whichever dimension is biggest for the irreducible components. That is also precisely the dimension of V. And now we define a dimension for Noetherian spaces, and we see that the Zariski topology is a Noetherian space. So now we get into the very natural definition. Dimension of an algebraic set is its dimension as a topological space under the Zariski topology. So as an example, we can talk, let's say, the simplest example, basically, the dimension of A is 1. Why is that? So what are all the algebraic subsets of A? There's only actually like two types, basically. One is A itself, and one are all the singletons. One are all the, specifically the irreducible. What are the irreducible algebraic subsets? So they're basically like since A is like algebraically closed, then there are only two types of irreducible algebraic subset of A, which is A itself and all the singletons, set with one element. And so because of that, no matter how you try, the longest we can possibly go is just A itself, and then perhaps a singleton, like say one or something. I don't know. Basically any singleton. So there's just one subset of an inclusion. So because of that, the dimension of A is basically just 1. Yeah, sure. Sure.
Yeah, we have a short break for 10 minutes. I'll come back to Hypersurfaces. So, yeah, all right, 10 minutes.
It's more dimension. Okay. Right. So now, we basically have like now that we have the concept of a dimension, in particular for today, there is like two things that we are interested in. That is like say what is the dimension of a element? So any good guesses? Yeah, yeah. That is basically the most straightforward guess, and you are correct. It is n. But it turns out proving this surprisingly requires a lot of work. And instead of what do you think? What do you think is the dimension of the hypersurface of a n minus one? That is also correct here. It's also basically have to set up some work to actually begin. Okay, so first, pretty simple. First, quite straightforward fact. So if let's say V is an irreducible algebraic set, and W is a proper irreducible no, it need not be irreducible. Is a proper let's just say algebraic subset of V. Then there is basically it's very straightforward to see that in this case, dimension of W is strictly less than dimension of V. This is basically because like let's say W, let's say one of these longest chains, actually basically just every chain, let's say W, W1, W2, and so on. That's because we can basically always just that's because we can basically just always append a V in front. So actually, if we go back and talk about Noetherian spaces in general, what we have in general is basically dimension of W plus 1 is less than or equal to dimension of V. And if this is finite, then it's pretty straightforward. That basically this is just dimension of W less than dimension of V. All right, so now we introduce something commutative algebra that is a very important concept for both in general and here. So now we let R be a ring, and let's say P is a prime ideal. Then we define P, the height of P is basically the supremum of the supremum of all the n's such that there is a chain. Let's see. This thing provides. So basically, it's like kind of a similar concept to the definition of Euclidean space. We basically now, but here this time we basically now just define it to be the supremum of the height of basically P. Basically, we define the height of a prime ideal P to basically be like the longest possible chain of distinct prime ideal subsets of this biggest prime ideal. And with this, we define the crude dimension. Did I pronounce it correctly? Okay, let's call it crude dimension. Okay, the crude dimension of R is then basically just the supremum of the heights of all the prime ideas in R. So basically, from a prime ideal, we define its height to be the longest possible chain, and then from there we define a crude dimension to basically be the longest among these heights of the prime ideals or prime ideals in there. So first we immediately relate it to this fact. If A is an affine algebraic set, then the dimension of A is equal to the crude dimension of KA. For this one, here we mean the coordinate ring. The coordinate ring of A. Which as we talked about last week, last week is basically just a polynomial ring modded ideal, obviously in this case just modded the ideal of A. Yeah. And this one is relatively straightforward. So basically, it's so this one is actually basically quite straightforward, and here's a proof. Okay, so if A is this algebraic subset, algebraic subset of A. So then this means we consider what are the irreducible algebraic subsets of A. That is to say, that is a closed subsets of A. So again, by Nostalensatz basically tells us that this is basically corresponding to the prime ideals. The prime ideals of the polynomial ring continue. And then this in turns basically corresponds to the prime ideals of Ka itself. So the base that basically just says that basically the dimension of A is basically the length of the longest So basically, it turns out that like if we ask for the so basically like irreducible algebraic subsets of A basically corresponds to the prime ideals of the prime ideals of the polynomial ring containing the ideal on A, which basically corresponds to the prime ideals of the coordinate ring of Ka. And because of that, the dimension of A here is basically the length of the longest chain of prime ideals in Ka, which is basically the cool dimension of Ka. So crew dimension and dimension of an algebraic set are basically like, in the end, they basically have this correspondence. Right. Next, we want to show. Next, if you remember transcendent degree, to briefly recall, like the transcendent degree of, like, say, like let's say K omega is basically like a number of elements in any transcendent space. Omega. Now it turns out that there is if A is an integral domain, K is a subfield A, then it turns out in general, what we have is dimension of A is actually less than or equal to the transcendent dimension of Q, QA, where QA means the field of fractions of A. So basically, it turns out that we have this fact, but right. But basically, in order to get to here, we'll be best if we set up some groundwork first. Okay, so we have this fact, but to actually try to prove it, we have to make some setup first. So if we let A be a commutative ring, and suppose further that X in A, then we define this particular set. I believe some people call it localization. I'm not sure. So yeah, it's basically just this quantity, n in N and is in A. Basically, it's basically this term, and it's in with all possible N and all possible A in A. And then, furthermore, we define the boundary. We define what is called the boundary of A at X to basically be the ring of fractions. Just now, basically like just heuristically, it's just this. And so, in order to prove this, we first prove another proposition first. That is, if we let A be a ring, Then it turns out that the dimension of A is less than or equal to n if and only if for any x in A, the dimension of this boundary of AX is actually less than or equal to n minus 1. This one I'll just give a kind of a proof idea because, to be honest, I'm myself not very sure this one. But basically, it basically uses this correspondence, like uh, specifically this correspondence just now. The prime ideas of A that are disjoint from S, and the prime ideals of S inverse A. Going back, basically the idea is that we can always show that for any x in A, and any maximal ideal of A, the M intersects this. And furthermore, if M is a maximal ideal, and P is a prime ideal contained in M, then it turns out that for any x in M complete M without P, then P intersects Sx. Well, P never intersects Sx, basically. So basically, it turns out we can basically show these two facts, and from here, we can these facts can basically just tell us that, like, so since, like, in some sense, since the maximal ideal and this Sx never always intersect somewhere, so that means that when we pass A to AX, which is basically AX, it's basically like, in some sense, we always end up quotienting this maximal ideal way. So, like, if we have like the concept is like you have like a chain, when you pass it here, like the maximal ideal is like in some sense just quotient away in that sense, I think. So this basically says that every chain of prime ideals beginning with a maximal ideal is basically shortened when passing from A to AX. And the second statement says that, like, this maximal a maximal chain of prime ideals, basically like all the prime, basically like a prime ideal that is like as long as possible. Like, let's say if it's n, it can be shortened to only n minus 1 if you can choose an appropriate x. So from here, it basically says like dimension of A. If it's less than or equal to n, it can be shortened. It basically like shortens to n minus 1 in that way. So basically, we're this back. So we can now go back to this. So we basically go back to this fact. I'll now rewrite here again. Okay, so this is the fact that we'd like to prove, because it turns out this fact basically can imply a number of other facts. So okay, so if the right hand side is infinite, like like let's say like CO2, this is in fact extension that is like this extension is in fact something like infinitely long travel, like the cardinality of the transcendent degree of CO2 is it's infinite basically, yeah. So in this case, obviously we do not have to care anymore. So we let it be n, and for to make it easier to compute, we basically only consider the case where k is like algebraically close in A, because like it should not affect the transcendent degree. Like algebraic extension should not affect the transcendent degree basically. So let x be in A, and so we have two cases. If x is not in K, then x is transcendental over K, or basically algebraically independent over K. So in this case, so basically like you can basically consider this basically it's just K and this X as the smaller subfield containing both X and K and X, and for brevity's sake, this is just notation. I'll just write KX here. So remember that entity just now, we can basically write it like this. Right. So one of them, it's N. And the other one, like it's basically transcendent degree. Like with one of them, there's this one is just appended an X into the field. So like this should be just one, because there's like just one transcendent. So basically, this basically implies that the transcendent degree of this one is in fact n minus one. And if you can recall, basically what we have is this field, okay, this field, it is actually a subset of AX, which is to say basically the quotient of which is basically the quotients of this. So basically, like the idea is that they basically perform induction. They perform induction that like assuming this holds for assuming this inequality holds for n minus like say a lesser n, that you can basically improve it. Yeah, I'm not honestly I'm a little bit lost, but basically like this eventually implies that this dimension of AX is less than n minus one. And that is for the x not in K case. So the x in K case is much easier. If x is in K, then 0 is in fact in the XX case, because we can just write it as x inverse times x. and then it's in SX. So this basically just means that, so it turns out this basically just implies that AX, since 0 is in SX, this actually basically implies that AX is actually just the 0, basically just 0. And so, well, so the dimension is also going to be, in particular, also less than n minus 1. So in either case, what we have is that the dimension of this is less than or equal to n minus 1. But this, of course, based on the equivalence we're given, this actually basically just means the dimension is less than or equal to n. All right. In fact, more than that, it's like we have this, but it turns out that if we further impose A is finitely generated, we further impose A is finitely generated, then in fact what we have is that the dimension of A equals to the transcendent degree of for this, I will not really be going through the proof, but it basically uses what is the Noether's normalization lemma. Yeah. So for those interested, I guess you can try to search it up and prove yourself. So now we can first answer the question. What is the dimension of AN? Well, it equals to n. And why? That is basically because Kan the dimension of AN is is basically equal to the crew dimension. The crew dimension. Oh yeah, just now when we say dimension, we mean basically crew dimension since we are working with rings. In any case, if you recall, the dimension of AN is basically the dimension of crew dimension of KAN. But this is basically precisely it's also precisely basically just the coordinate, the polynomial ring. Polynomial ring of x1 to xn. And this crew dimension of this thing in turn, it's basically just they are just x1, x2, the transcendent basis. So we in fact just have n. In fact just n here. So it turns out the dimension of AN is basically just it's basically just n here. Yeah. And now what about a hypersurface, which we talked about just now? Well, it is in fact given as n minus 1. So what we do here is we basically let's say let's say we have Yeah. So if we have to prove it, okay. With let k, we consider this to equal like the polynomial ring modulo the uh, okay. And we consider like the field of fractions. Okay, x1, x2. Now, since like f is not the zero polynomial here, so there is like say so there is like at least one of these x1 to xn terms occurs inside of it. Let's say xn is in xn occurs in then actually it basically follows that xn occurs in every non-zero multiple of f. And because of this, I believe that in fact the x1, x2, or until xn minus one, they must be algebraically independent. Algebraically independent for this near k. But on the other hand, since what we have is basically like this polynomial before, this means that xn itself in turn is algebraic over k x1 x2 and until xn minus 1. So to put it all together, this basically means that x1 x2 and until x minus 1 is a transcendental basis for k x1 x2 until xn minus 1 over k. And this basically by this transcendental degree result, this basically says that the dimension of this hypersphere is n minus 1. Okay, so we actually answered is that the dimension of hypersphere is n minus 1. But we can in fact actually show something. At least for an, it turns out that any variety, any algebraic set actually, the dimension n minus 1 must be a hypersurface. So how do we see this? Actually, we show a more general fact. That is that if we let V be an algebraic set, dimension n W is an algebraic subset with dimension n-1. Then, if the field, the subfield with k and v, if the coordinate, if the coordinate, if the coordinate ring of kv is a unique factorization domain or UFD. So, a reminder is basically like it's basically a ring that basically has the property of like having a unique multiplication for any non-units that has a unique factorization method. Like if you remember the fundamental theorem of arithmetic for natural numbers, yeah, UFD is a generalization of that. And if KV is a UFD, this means that this ideal is basically then the ideal of W is actually just a single F generator, a single principal ideal generated by F for some KB. Or in other words, this is equal to W is a hypersurface. All right. So we let W's be the irreducible components. Irreducible components of W. Then it turns out if you recall, this basically just says like one union to W S. But if you recall from week 1 results, this is basically just the intersection of all this WI basically. So we can if we can show that one of these is basically so basically we can show that we can just assume here that W is irreducible. All right, and we put P equals to IW here. So of course, since W itself is irreducible, this means that P is a prime ideal, and P is not the zero ideal, because this would otherwise contradict the fact that dimensional W equals to dimension V, even though one is n-1 and one is n. So that means that it must contain an irreducible polynomial. Then this one is a UFD result, if I remember correctly. That is, this F is a prime ideal as well. So we claim that basically this is in fact the idea of W is in fact F. And to do this, we assume for contradiction that P is not equal to this ideal generated by F. So this means that we have this chain That means we have this chain here. And if we take the zero set, this basically means that we have V yeah, and VP. But this is basically just W again. But recall that these are in fact irreducible algebraic sets. So this means that we have basically the dimension of W strictly more than dimension of BFF, and this is more than W. But of course, this is a of course, there I guess. Let me check it out. Set. Let me check my sources real quick. Yeah. Yeah. I'm not sure if I did everything correctly, but yeah, I'll leave it as an exercise and check basically if there's any mistake in it. Right. So basically, in conclusion, what I basically have that is that in AN, any algebraic set with dimension n-1, they're basically surfaces. And yeah, this is basically tying hypersurfaces and dimension together. And yeah, that's basically all the part that I have to say here. So yeah, thank you all for listening.
Thank you all for coming today. So yeah, we managed to define dimensions and look at it algebraically. So yeah, we'll stop here for now, and then the next seminar will be next Thursday. Right, see you then. Right, thank you. Wait, Darren. Darren, so to your thoughts. You go.